We're designing Airbnb, a global platform connecting millions of hosts and guests. It needs property listings, search, booking with payment processing, reviews, and messaging. The system must handle 10 million active users across multiple regions, prevent double bookings with strong consistency, deliver search results in under 500 milliseconds, and maintain 99.95% uptime with PCI DSS compliant payments. Let's start with the MVP architecture for Airbnb. We have a simple monolithic web server handling all requests from web clients. The server connects to a PostgreSQL database that stores everything: property listings, bookings, user profiles, and payment records. We also use Amazon S3 for storing property images. This straightforward architecture supports basic CRUD operations and can handle around 10,000 users comfortably. It provides all core capabilities: listing properties, booking properties, managing user profiles, and processing payments. This is perfect for early market validation with minimal complexity. As we approach 1 million users, the MVP architecture hits critical bottlenecks. Database reads become a major problem as users constantly browse listings. To address this, we introduce several key components. First, we add a load balancer to distribute traffic across multiple web servers, providing horizontal scalability. We deploy RED replicas for the PostgreSQL database to handle the heavy read load from listing queries. We introduce Elasticsearch for fast, low-latency search with complex filters like location, price range, and amenities. Redis cache stores hot listings and frequently accessed data, dramatically reducing database hits. A CDN delivers property images globally with low latency. Finally, we add a message queue for asynchronous tasks like sending booking confirmations and notifications. This architecture can now handle 1 million users while maintaining search latency under 500 milliseconds. At 10 million plus users, the monolithic architecture becomes completely unmanageable. We transition to a microservices architecture with clear service boundaries. We now have dedicated services: listing service manages property data, booking service handles reservations with strong consistency to prevent double booking, payment service integrates with Stripe and PayPal using idempotency keys for reliable transactions and PCI DSS compliance, search service uses Elasticsearch for fast queries, messaging service enables host-guest communication, and user service manages profiles and authentication. We introduce Kafka as our event streaming platform for event-driven architecture. When a booking is made, events flow through Kafka to update availability, trigger notifications, and sync data across services. We use Postgres for efficient geospatial queries to find properties near a location. Redis cluster provides distributed caching for session management and availability checks across multiple regions. Each microservice has its own database following the database per service pattern. Cassandra stores chat messages for high write throughput. This architecture achieves our non-functional requirements. It supports 10 million plus active users globally, maintains strong consistency for bookings, delivers search results in under 500 milliseconds, provides 99.95% uptime through redundancy and failover, and ensures PCI DSS compliance for payment processing. Let's dive deep into the booking system, which is the most critical component of Airbnb. This system must prevent double booking at all costs while maintaining high availability. The architecture consists of an API gateway routing requests to specialized services. The booking service handles reservation logic and uses PostgreSQL for ACID transactions, ensuring strong consistency. The payment service coordinates with Redis for distributed locking during payment processing. The critical requirements are clear: absolutely no double booking, strong consistency for availability updates, and idempotent operations to handle payment retries and network failures safely. The first major trade-off is between pessimistic and optimistic locking. Pessimistic locking uses select for update to acquire a database lock immediately. This guarantees no conflicts but severely limits throughput since other requests must wait. Optimistic locking reads a version number, performs the operation, then updates only if the version still matches. This allows high throughput but requires retry logic when conflicts occur. For Airbnb, the choice is context dependent. Booking operations use pessimistic locking because preventing double booking is critical and booking volume is manageable. Search and browsing use optimistic locking to handle high query volume efficiently. The second critical trade-off is between database transactions and distributed locks. Database transactions provide ACID guarantees with automatic rollback and configurable isolation levels. They're perfect for operations within a single database like booking creation and availability updates. However, they don't work across multiple services. Distributed locks using Redis enable cross-service synchronization with TTL expiration for safety. But they require manual cleanup and are vulnerable to network failures. Airbnb uses database transactions for core booking operations where ACID guarantees are essential. Distributed locks coordinate payment processing and external API calls that span multiple services. This hybrid approach balances consistency with scalability. The third trade-off is synchronous versus asynchronous booking confirmation. Synchronous processing checks availability, processes payment, and confirms the booking all in one request. This takes 3 to 5 seconds but gives users immediate feedback. Asynchronous processing queues the request, returns instantly, then sends an email confirmation later. This is faster but creates uncertainty for users. Airbnb chose synchronous confirmation because users expect instant feedback when booking expensive accommodations. The 3 to 5 second wait is acceptable for the peace of mind of knowing your booking is confirmed immediately. Async would be faster, but the uncertain outcome hurts user experience. The fourth critical design decision is idempotency strategy. When a user clicks book, the request might time out due to network issues. The user retries, but the first request actually succeeded on the server. Without idempotency, this creates a double booking disaster. The solution is idempotency keys. The client generates a unique UUID for each booking attempt and sends it in the request header. The server checks if this key already exists in the database. If it exists, the server returns the cached result without processing again. If it's new, the server processes the booking and caches the result with that key. This ensures that retrying the same request multiple times has the same effect as making it once. Idempotency is essential for payment processing where duplicate charges would be catastrophic. Now let's explore the search engine, which drives 80% of user interactions on Airbnb. The architecture routes search queries through a search API to an Elasticsearch cluster. Elasticsearch is optimized for full-text search with inverted indexes and geospatial queries. The ranking algorithm is complex, balancing multiple factors. Relevance score accounts for 30%, matching the query to listing descriptions. Price competitiveness is 25%, favoring listings with good value. Host rating contributes 20%, prioritizing highly rated hosts. Booking history adds 15%, boosting listings with strong conversion rates. Finally, promoted listings get a 10% boost, allowing hosts to pay for better visibility. This multi-factor ranking balances user experience with revenue optimization. The first major trade-off for search is Elasticsearch versus PostgreSQL full-text search. Elasticsearch uses inverted indexes optimized for full-text search, geospatial queries, and complex aggregations. It scales horizontally and delivers queries in 50 milliseconds. However, it's eventually consistent and requires a dedicated cluster, increasing cost. PostgreSQL offers basic full-text search with GIN indexes and PostGIS for geospatial queries. It's strongly consistent and uses existing infrastructure, keeping costs low. But queries take 200 milliseconds and scaling is limited. Airbnb chose Elasticsearch because search is the primary user interaction. The 4 times faster query speed and superior ranking capabilities justify the additional infrastructure cost. Eventual consistency is acceptable since search results don't require real-time accuracy. The second trade-off is real-time versus batch indexing. Real-time indexing updates Elasticsearch immediately when a listing changes, using Kafka events to trigger index updates within 1 second. This keeps data fresh but causes high CPU load and index churn as the cluster constantly rebuilds segments. Batch indexing collects changes and bulk indexes every 5 minutes. This is efficient and reduces CPU load, but data can be stale for up to 5 minutes. Airbnb uses a hybrid approach. Availability updates are indexed in real time because users need accurate availability when booking. Description changes, photos, and reviews are batch indexed every 5 minutes since slight staleness is acceptable. This balances freshness with cost efficiency. The third trade-off is geospatial query strategy. Bounding box queries filter by latitude and longitude ranges, creating a rectangle around the search area. This is fast and uses simple indexes but includes corner areas outside the actual search radius. Radius queries calculate exact distance from a center point, creating a perfect circle. This gives accurate distance but requires complex geospatial indexes and slower queries. Airbnb uses a two-stage approach. First, a bounding box quickly filters to a superset of results. Then, radius calculations rank results by exact distance and filter out corner areas. This combines the speed of bounding boxes with the accuracy of radius queries. Let's explore how to build an Airbnb scale platform on AWS. Here's our complete architecture designed for global reach, high availability, and seamless user experience. Starting at the entry point, we use Route 53 for DNS management with health checks and CloudFront as our CDN to deliver static assets with sub-50 millisecond latency worldwide. API Gateway handles request routing and rate limiting, directing traffic to our application load balancer. This combination ensures users get fast, reliable access from anywhere. Moving to our compute layer, we run microservices on EKS with Kubernetes for container orchestration, giving us autoscaling and zero downtime deployments. ECS Fargate hosts our web servers, eliminating server management overhead. For event-driven workflows like booking confirmations and notifications, we use Lambda functions triggered by SQS and SNS, processing millions of events daily with automatic scaling. Now let's examine our data layer. RDS PostgreSQL with PostGIS powers our geospatial queries for location-based searches, with multi-AZ deployment for 99.95% availability. Read replicas handle search traffic, while Elasticache Redis cluster provides distributed caching with microsecond latency. OpenSearch service enables full-text search across millions of listings. For photos and documents, S3 stores petabytes of data at just 2 cents per gigabyte. MSK handles real-time event streaming for analytics and recommendations. Taking a step back, this architecture handles millions of concurrent users with automatic scaling, costs approximately $15,000 to $25,000 monthly at moderate scale, and can grow to support billions of requests. Tools like Clouda.ai can help you design and optimize architectures like this, with built-in AWS best practices, real-time cost analysis, and automated compliance checks. Whether you're building the next Airbnb or modernizing existing systems, proper architecture planning ensures you scale efficiently while controlling costs. We designed Airbnb from MVP to 10 million users. Key decisions: distributed booking system with locks and idempotency, Elasticsearch for geosearch, and multi-region cloud deployment. Start with MVP using PostgreSQL. Add Redis caching at 100K users. Deploy Elasticsearch when search becomes critical. Scale globally with CDN and multi-region architecture.